Okay, so you know how it is, right? Like you're trying to keep up with everything that's happening, all the new stuff, but it feels like you're just constantly bombarded with information.
Yeah,
Like
definitely.
trying to drink from a fire hose.
Right. Just too much. You can't possibly get through it all.
Exactly, and trying to sift through it all, trying to figure out what actually matters. It's
Yeah,
exhausting.
you spend all this time, and then you wonder if you really learned anything that's, going to stick with you.
Totally. And that's why we do this. This is the deep dive. We're taking those piles of articles, research papers, whatever it is.
Yeah, we try to get to the bottom of it.
Yeah, extract the real insights, the stuff that'll actually make you feel like you've learned something without getting bogged down in every little detail.
Right, like we're doing the heavy lifting so you don't have to.
Exactly. And today we are diving into something that has the potential to completely change how we think about AI.
Oh, yeah.
Yeah, a new way to evaluate and train AI models. Specifically, we're talking about self-principled critique tuning.
Okay, SPCT. I've seen that acronym floating around.
Exactly. It's all about these large language models, Those AI that can understand and generate human-like text, like really impressive stuff.
Right, like ChatGPT and all those.
Yeah, exactly. And our main source for this deep dive is a paper called Inference-Time Scaling for Generalist Reward Modeling. So our mission today is to really understand SPCT and why it's creating so much buzz in the AI world, why people think this could be such a big deal.
Right, so what's the core problem that these researchers are trying to solve with this whole SPCT thing?
Okay, so imagine this, right? You have these incredibly powerful LLMs that can do amazing things.
Like write poems, translate languages,
Yeah.
and I don't know, write code or something.
Yeah, exactly. But a lot of the really impressive progress we've seen with these models has been in areas where there's a clear right and wrong answer,
I see.
like solving math problems, writing code. There are rules, very specific rules, so you can easily tell if the AI got it right or wrong.
Makes sense.
But what happens when you want the AI to answer a more open-ended question? Something that requires general knowledge, understanding of the world, some nuance in its reasoning.
Ah, I see. So it's not just about spitting out the right formula or the right line of code. It's about,
It's about understanding and responding in a way that a human would. And that's where things get tricky with evaluating these models. How do you tell if they're doing a good job?
right, because there's no one single correct answer anymore.
Exactly. And that's where this idea of reward modeling, or RM, comes in. It's a core part of how we train LLMs using something called reinforcement learning.
Okay, reinforcement learning, I've heard of that. It's like rewarding the AI when it does something good, right, to guide its learning.
Exactly. So think of reward modeling as kind of like the AI's internal compass, It helps the AI understand what constitutes a good answer or action.
So by giving it a reward signal when it does well,
Precisely, like, you did good, have some virtual points, keep learning in this direction kind of thing. But the paper points out that current reward modeling techniques, well, they've got some limitations.
oh, no way.
Well, let's take scalar RMs, for example. These models assign just a single numerical score to the AI's response. So like, say, a 7 out of 10. But the problem is that a single number can't really capture all the different aspects of a good answer. It's too simplistic, Like trying to judge a whole movie based on just giving it a thumbs up or thumbs down.
Yeah, you lose all the nuances, the things that actually make it good or bad.
Exactly. And on top of that, these scalar models don't really benefit from using more computational power at the moment of answering. It's like, if you ask someone for their opinion on something and they give you a one-word answer, and then you ask them again, hoping they'll elaborate, but they just repeat the same word.
You're not going to get much more information out of them now.
Exactly. So then you have pairwise RMs, and they compare two responses at a time. And while that can be useful in some cases, it's not very flexible. What if you want to evaluate a single response on its own? Or what if you have multiple responses you want to compare all at once?
Right, pairwise models are kind of limited in that sense.
Exactly. Then there are generative RMs, and these are more adaptable because they can actually generate full text critiques. They can explain what they think about the response.
Oh, interesting. So instead of just a score, you get an actual explanation.
Yeah, exactly. But the paper highlights that even these generative RMs haven't really figured out how to effectively use more computation at the moment of answering to really refine those evaluations. Like they're not taking advantage of the extra processing power they could have.
Okay, so we've got all these different ways to provide feedback to AI, each with its own strengths and weaknesses.
Right. And that brings us to point-wise generative reward modeling, or GRM, which is the foundation for this new approach the researchers are proposing.
Right. Point-wise GRM. What makes this one stand out?
Well, the big thing is its flexibility. Point-wise, GRM can handle all those different input formats we talked about: a single response, a pair of responses, even multiple responses.
Hmm.
And it does this all within the same framework, using language to express its evaluations. So instead of just a number, you get a critique.
Oh, I see. So it's like instead of just saying this is a 6 out of 10, it might actually say something like this answer is accurate, it's well structured, but it could benefit from including more recent data.
Yeah, exactly like that. That's way more useful than just a number, right?
Absolutely. It's way more actionable. You can actually do something with that feedback.
Precisely. Now, building on this, the researchers started exploring the idea of using principles to guide this reward generation process. So moving beyond just rigid rules, you know?
Principles. Interesting.
Yeah, so like guidelines or general criteria for what makes a good response. And what they found was pretty interesting. At first, they tried just letting the AI generate these principles completely on its own, but that didn't really improve things.
So just letting the AI make up its own rules didn't work.
Not quite. But then they tried something different. They had the AI generate these principles, but then they carefully selected or filtered the ones that seemed most useful.
Oh, so they added a layer of human judgment to the process.
In a way, yeah. And what they found was that these filtered principles could actually significantly improve the quality of the rewards the model was giving.
Okay, so there needs to be some kind of selection process, some filtering. Just letting the AI run wild with its own principles isn't enough.
Exactly. And that brings us to the heart of this paper, the really innovative part.
Right.
Self-principled critique tuning, or SPCT.
Okay, SPCT. Lay it on me.
So SPCT is a two-stage learning process specifically designed to make these point-wise generative reward models much better at coming up with their own effective principles and critiques. And that ultimately makes the reward generation much more powerful and scalable when the AI is actually evaluating responses.
2 stages, you say. Tell me more about them.
All right, so the first stage is called rejective fine-tuning, or RFT. Think of this as the initial training phase for the model.
Okay, got it.
And the goal here is to teach the generative reward model how to produce principles and critiques in the correct format. So how to give feedback in a way that makes sense, whether it's dealing with a single answer, a pair of answers, and so on.
So it's learning the language of giving good feedback.
Exactly. And they're using this point-wise GRM approach for all those different scenarios right from the start. Now, the rejective part of the name comes from how they handle the training data. So what they do is they generate a bunch of AI responses along with principles and critiques for those responses.
Okay.
And then they look at these whole sequences, these trajectories. So a trajectory is like one complete attempt at answering a question, including the AI's reasoning and everything. They look at these trajectories, and if the predicted reward for a trajectory doesn't match up with what they know to be the best answer.
So they throw it out.
Exactly. They reject it. And they also reject cases where the AI is getting it right too easily, too consistently.
Too easy. Why would they reject that?
Because it seems like if the task is too easy, the model isn't really learning anything useful. You know, it's not being challenged. So they're really trying to focus the learning on the situations where evaluating the response is actually difficult.
That makes sense.
Yeah.
It's like if you're trying to learn a new skill, you don't want to keep practicing the stuff you already know how to do perfectly.
Exactly. Now, they also use something called hinted sampling sometimes. So in certain cases, they'll give the AI a little nudge, like a hint about which response is better, to help it learn how to generate useful principles and critiques in the first place.
So they're kind of giving it some training wheels at the beginning.
Exactly. But what's interesting is that they later found that the learning the AI did without these hints was actually more valuable in the long run.
Oh, really? So those training wheels might actually hold it back in the end.
It seems that way, yeah. Okay, so that's RFT, the first stage. It provides that foundational learning, teaches the model how to structure its feedback, and it focuses on the more challenging evaluation cases.
Okay, makes sense. So what about the second stage?
So the second stage is called Rule-Based Online RL, where RL stands for reinforcement learning. And this stage is all about making the GRM better at generating high-quality, generalizable rewards.
Okay, so it's getting more refined in the second stage.
Exactly. So what they do here is they use accuracy rules to reward the GRM when it correctly identifies the best response based on the principles and critiques it's come up with.
Wait, so the AI is getting feedback on its own feedback. That's kind of meta, isn't it?
It is, right. It's like having the AI grade its own homework and then getting graded on how well it graded itself.
Wow.
Now, instead of directly rewarding the model for the format of its critiques, they use something called a KL penalty.
KO penalty.
Yeah, it's a bit technical, but basically think of it as like a gentle nudge to keep the AI's feedback consistent and focused. So it prevents the model from going off on irrelevant tangents or getting too verbose or anything like that.
Oh, I see. So it's like, hey, stay on topic, keep it concise.
Exactly. And the main goal of this whole stage is to train the GRM to become really good at distinguishing between good and bad responses, and importantly, being able to justify its reasoning through the principles and critiques it generates.
So it's not just about saying this is good or this is bad.
Yeah.
It's about explaining why.
Precisely. All right, so we've got these two phases, RFT to get things started and RL to refine the model's ability to generate principles and critiques. Now let's talk about that inference time scaling that's in the paper's title.
Right, inference time scaling. What exactly does that mean in this context?
So it basically refers to the ability of the reward model to improve just by using more computational power when it's actually evaluating responses. So like if you give it more time to think, it can come up with a better evaluation.
Oh, interesting.
Yeah.
So it's not just about how much training data you feed it. It's also about how much computational power it has when it's actually working.
Exactly. And DeepSeek-GRM, the model they developed using SPCT, it leverages inference time scaling in a couple of really interesting ways.
Okay, tell me more about that.
So the first way is through something they call voting with generated reward.
Voting, like an election for the best answer or something.
Kind of, yeah.
Yeah.
So basically, when DeepSeek-GRM is evaluating a set of responses, it doesn't just do it once. It actually samples multiple times, meaning it generates a different set of principles and critiques for the same input each time it evaluates. And then for each response, it adds up the individual rewards it assigned across all those different evaluations. So it's like getting multiple opinions on the same answer and then combining them into a final score.
Oh, that's clever. So by generating multiple sets of principles and critiques, you get a more robust and comprehensive evaluation.
Exactly. The researchers point out that this expands the reward space, meaning it can make more nuanced judgments based on a wider variety of judgment perspectives.
That makes sense. It's like if you only ask one person for their opinion, you're only getting one perspective. But if you ask multiple people, you get a more well-rounded view.
Precisely. And to avoid any biases, they randomly shuffle the order of the responses before each sampling round. So it's not just favoring the response it sees first, for example.
That's smart. They've really thought this through.
They have. Okay, so that's the first way they achieve inference time scaling. Now, the second method is called meta-reward modeling guided voting. And this takes the idea of quality assessment to a whole new level.
Meta-reward modeling, what is that?
So what they do is they train a separate meta-RM, basically another reward model.
Yeah.
And this meta-RM is specifically designed to assess the quality of the principles and critiques generated by the main DeepSeek-GRM model.
Wait, so it's like having an AI judge for the AI judge?
Exactly. It learns to identify which principles and critiques are likely to be the most accurate and helpful, the most reliable.
Wow, that's amazing.
And then this meta-RM guides the voting process. So instead of just adding up all the sampled rewards equally, it gives more weight to the evaluations that came from what it deems to be higher quality principles and critiques.
So it's like, these opinions are more trustworthy, so we'll give them more weight in the final decision.
Exactly. And this leads to even better scaling performance because you're prioritizing the more reliable judgments. Interestingly, they trained this meta-RM using data from that initial RFT stage and also using samples from the DeepSeek-GRM itself. So it's learning from the best of both worlds in a way.
That's really cool. So they're really trying to ensure the evaluations are as accurate and as unbiased as possible.
Exactly. Now, all this sounds very promising in theory, but did it actually work in practice? What were the results of their experiments?
Well, they tested DeepSeek-GRM on various established reward modeling benchmarks, and the results were very impressive. Their model, DeepSeek-GRM 27B, that's the one they trained, with 27 billion parameters, it actually outperformed existing baseline methods. And it even achieved results that were competitive with much larger publicly available models.
Really? Like how much larger?
We're talking hundreds of billions of parameters larger. Models like Nematron 4340B Reward and GPT-4o.
Wow. So even though DeepSeek-GRM is smaller, It's still able to hold its own against these giants.
Exactly. And it wasn't just about the overall performance either. They also found that the traditional, scalar and semi-scalar reward models, they tended to show quite a bit of bias across different types of tasks.
Oh, in what way?
Like, they might do really well on those very clear-cut tasks, like the math problems and code generation we talked about earlier, but then they would struggle in areas where there's more nuance and interpretation involved.
I see. So they're kind of specialized, whereas DeepSeek-GRM seems more well-rounded.
Exactly. It demonstrated a much more consistent ability to generate good rewards across a wider range of scenarios. They even compared it to this LLM as a judge approach, which showed similar biases but generally lower performance overall. And they think that might be because it lacks that explicit guidance from the principals during its training.
So SPCT leads to a more generalizable reward model, it seems. What about that inference time scaling? Did they see improvements there?
Or absolutely. Figure 1 in the paper really highlights this. It shows how the performance of different reward models changes as you increase the number of samples you take during evaluation.
Yeah.
And DeepSeek-GRM 27B, it showed the most significant gains. Its performance just kept getting better as they increased the samples, all the way up to 32. And then when they added that meta-RM guidance on top of that...
It got even better.
Exactly. Those improvements became even more pronounced. They compared this to another model, CloudGemma 227B, which is a semi-scalar RM. And it showed very limited improvement with more samples because its basic reward score, the number it was assigning, it didn't really change that much, even though its critiques were changing.
Interesting. So it's not just about having more samples, it's about how those samples are used, how they're weighted.
Exactly. And they also pointed out that when they used a technique called token probability voting with LLM as a judge, that's basically a way to use more detailed numerical weights in the evaluations. Its performance also went up. So again, it seems like having more quantitative information to work with really helps.
So more samples, intelligently weighted, using that meta-RM, it all contributes to DeepSeek-GRM's impressive scaling performance.
Precisely.
The paper also mentions some ablation studies. Can you tell us a bit about those and what they revealed?
Yeah, so ablation studies are basically a way to figure out which components of a system are actually contributing the most to its performance. And their findings were really insightful. One surprising thing they found was that even if they skipped that initial RFT cold start phase, the online RL phase still led to significant improvements.
Boy.
Yeah, which means that reinforcement learning phase is really crucial. That's where the model really learned how to generate good rewards. They also found that the learning that happened without those initial hints in RFT, that was actually more important than the learning with the hints.
So it's like those training wheels we talked about earlier. Taking them off forces the model to learn more effectively.
Exactly. And those studies also confirmed that having a lot of general instruction data is very important for training these generative reward models.
Yeah.
And they show that the ability to generate principles was really essential, both for getting good performance with a single evaluation and for that inference time scaling. Oh, and one more thing. They also showed that the meta-RM guidance was effective even when they changed how many of the top-rated samples they were using.
So it's a robust approach, it seems. All these different components really work together to make SPCT effective.
That's right.
Now, what about the computational cost of all this? Is this a more efficient approach compared to just using bigger and bigger models?
Well, they did analyze the scaling of both inference and training costs, and they found something really interesting. Figure 4 in the paper shows that DeepSeek-GRM 27B, when it uses inference time scaling with, say, 32 samples in direct voting, or even fewer samples when using meta-RM guidance, it could actually achieve comparable or even better performance on this benchmark they call reward bench compared to a much, much larger model.
Really? How much larger are we talking?
This other model, DeepSeek V3, it has 671 billion parameters. That's like more than 20 times larger than DeepSeek-GRM 27B.
Wow. And the smaller model, using inference time scaling, was able to outperform it.
Yeah, which suggests that maybe we don't need to keep building these massive, incredibly expensive models if we can figure out smarter ways to evaluate their responses.
That's a huge takeaway. It could change how we approach AI development in a big way.
Right. It indicates that intelligent use of computation at inference time could be more effective than just blindly scaling up the model size. And they had another interesting finding. They had this model called DeepSeek-R1, which is specifically designed for really long step-by-step reasoning.
Okay.
And it actually performed worse than a smaller RFT-trained model on those general reward modeling tasks. So it seems like just making the AI think longer and harder isn't necessarily going to lead to a better reward model.
So quality over quantity when it comes to reasoning, it seems.
Exactly.
So to sum it all up, what would you say are the big takeaways from this research on SPCT and DeepSeek-GRM?
Well, I think this research shows a really promising new direction for how we evaluate and train large language models. Self-principled critique tuning enables these generative reward models to get much better at understanding what makes a response truly high quality, and it does that across a wide range of different tasks. And by using increased computation at inference time in a smart way, especially with that meta-reward model guidance, they've shown that it's possible to achieve more accurate and reliable evaluations without just relying on bigger and bigger models. It's a step towards more efficient and more broadly applicable AI development.
So the aha moment here is that we can enable AI to essentially create and refine its own standards for what makes a good answer through these principles. And then by being smart about how much computational power we give it when it's making judgments, we can build these much more robust and flexible reward systems.
Exactly. It's about moving beyond brute force and towards more intelligent and efficient approaches.
Absolutely. As we wrap up this deep dive, do you have one final thought you'd like to leave our listeners with? Something to ponder.
I think the big question to consider is this. If we can scale up the evaluation process at inference time like this to get those more nuanced and reliable judgments, how might that change not just how we train AI, but how we interact with and trust AI systems in the future? Could we, as users, maybe leverage similar techniques to get more insightful and trustworthy responses from AI when we're asking those complex, open-ended questions?
That's a fascinating thought. It really opens up a lot of possibilities, not just for how we develop AI, but for how we use it in our everyday lives. For those of you who want to explore this further, we highly recommend checking out the research paper itself. It's called Inference-Time Scaling for Generalist Reward Modeling by Liu et al. And digging into the concepts of reinforcement learning, reward modeling, and the evaluation of large language models will give you an even deeper understanding of this really exciting work.
Keep diving deep.